Last time we started talking about the combined cycle power plant. This is that type of power plant. The fuel is natural gas. You put it first through a Brayton cycle. So right here is the combustors. If you just look inside this illustration of a power plant, the gas turbine, and then the flue gas comes out. It's hot. It expands out into a large heat recovery steam generation unit, and then finally after that out the flue. The shaft of this is connected to an electric generator, and over here it looks like these are some steam turbines that are also connected to the same shaft, and so there's a lot of piping that runs back to the steam turbines. Also, there'll be some piping running out to, what are these right here? Yeah, they're heat exchangers. They're mechanical draft. There's a big fan that draws air through, and they have water that's splashing down, and so it's an evaporator that provides the cooling. Typically, that's not the same fluid that's going through the steam turbines. It's probably a separate heat exchanger somewhere in here, where you have 2 water loops to transfer the heat, because a lot of this water is evaporating. It has to be replenished. It's still kept clean, but not to the level of the chemistry that's needed for the water that goes through the tubes in your steam generator and boilers, as well as through the steam turbine itself. So when we want to use natural gas as a primary fuel to generate electricity, state of the art is you do it in a combined cycle plant. So you have the combustor and the natural gas plant, the topping cycle, the Brayton cycle, followed by the bottoming vapor power cycle, Rankine cycle. And this makes it very simple. You need to be able to solve a problem like this, marching through and solving it for your homework problems, okay? Let's take a look at some videos. Notice that they're going to start talking about what is the achievable thermal efficiency of these plants. That's phenomenal. That is very high compared to a simple cycle power plant, which means you just had the Brayton without any boiling of water with the bottoming Rankine cycle combined, right? And so let's take a look at this video. Let me see. I do this.
60% plus. This is...
There's a couple points probably worth pointing out right here. Reductions in CO2 emission used to not be an issue, but it's going to be more of an issue in your lifetime. CO2 is what we want in combustion. We don't want CO. We don't want carbon monoxide. We want carbon dioxide. It's safe to breathe, etc. A lot of things. Why do you have less CO2 emissions for this type of power plant versus a coal power plant? Well, in a coal, the fuel is primarily coal, which is primarily carbon with no hydrogen. What is natural gas? What is methane? 1 carbon, how many hydrogen? 4. So you get a lot of water. It's just because the fuel is CH4 instead of all C. So as an engineer, it's like, well, that's just the makeup of the fuel. So you get more kilowatt hours of electric energy out per CO2 emission. All right. It's very clean, and we'll look at how to clean up nitrous oxides. You don't want those to go out your stack. That basically makes ground level ozone and is not good to breathe. The brown haze in the summer. Let's take a look at another video.
Using gas, oil, and other fossil fuels, the combined cycle GUD process synthesizes high efficiency and environmental protection as no other form of...
This is a plant that has 1 shaft. Go ahead and watch it. It's only 4 minutes.
Product of EcoMag.
All right, one more.
Boxes.
It's
Box
only 3
number 1
minutes.
is located closest.
Let's talk about aircraft propulsion systems. An aircraft engine like this is a turbofan. You've probably flown in aircraft, and that's what's under the wing. providing the propulsion. How does it work? It's based on linear momentum and it generates thrust. I'm going to ask you in a minute to write down how it works, okay? So basically here we have an air inlet through a compressors. Notice this getting smaller, higher pressure. Then it goes through the combustor. Not all the gas goes through into the combustor. A lot of it helps center the flame, and then it's mixed, and so it's lower temperature when it goes through the turbine section. The turbine section, it produces just enough power to run the compressor. There's no shaft feeding out, right? And then what do you have? You have still a very high pressure right in here, high pressure and high temperature, and you put it through a nozzle section such that you have a high velocity on the exhaust. Okay? You're probably videoed out, but this is, do you want to see this next time or now? Well, I hope you found that interesting. Let's go back to here. I have a question for you. I would like you to pull out a piece of paper. I'd like you to write down the answer to this question. Put your name on it and turn it in. I want you to describe how does a person calculate the jet engine thrust. And you might want to start by defining thrust. What's thrust? And then how do you calculate it? All right, so I'm going to stop here. I mentioned I put out on the Blackboard Learn GasTables add-in, so you can get that file and add it into your Excel file on your PC. It allows you to evaluate specific heats for different fluids at different temperatures. Also, the temperature-dependent internal energy, enthalpy, and S0, low pressure entropy, are all done for not just air, but carbon monoxide, carbon dioxide, water, vapor, nitrogen, and oxygen. So these have all of the help functions built in already. It's just these that I recently coded up that don't.